In this video, we're going to look at starter question 6. We're going to break this up into two parts. We're going to look at part A and then we'll look at part B in a second. Now in this question, we've got a curve and a line, and we can see that in the diagram above. You're told the equation of the line is y equals 5 minus 3x, and the equation of the curve is y equals 20x minus 12x squared. And they intersect at points P and Q, as you can see on the diagram. We're going to find what those points of intersection are. Then when we want to see where the curve and line intersect, we're going to need to use simultaneous equations to solve them. Now, both of these equations are already written in terms of y, so it makes it nice and simple that I can just simply set them equal to one another, as so. Okay, because when they intersect, their y coordinates are the same, so I can just set them equal to each other as so. Then what I'm going to do is I'm going to rearrange this to get a quadratic. So I'm going to add 12x squared to both sides, and I'm going to take away 20x from both sides. Now I need to solve this quadratic equation. Now you can do this a variety of ways. You could use the quadratic formula, you could complete the square, you could even use your calculator if you weren't sure. But it might not look like it, but we can actually factorise this. It might look like a tricky one, but it's not as bad as first looks. And the reason why, sorry, this should be a plus 5 here. Okay, so that's a plus 5 there. The reason why we can do this is because 5's a prime number and you've also got minus 23x. So I know that I need a minus 1 and a minus 5. That's the only two things it could possibly be. Then I go through the options of how I can make the 12x squared. So think about numbers that multiply together to make the 12. And if I put a 4x here and a 3x here, then I am going to get that minus 23x. So what this means is my x coordinates, I have x equals a quarter and x equals 5 over 3. So those are my x coordinates, but I need to find the y's as well. So now we just simply substitute into y equals 5 minus 3x. Okay, I'm going to sub it into the equation of the line because it's going to be a little bit easier than subbing it into the quadratic instead. So I sub x equals a quarter into y minus 3x, and when I do so, I get 17 over 4. Sub in the 5 over 3 into y minus 5 minus 3x, and I simply get 0. And that makes sense. 5 over 3 is bigger than a quarter, and you can see from the diagram here, I would expect 0. Okay, it's crossing the x-axis here when x is 5 over 3. So that makes sense that I get y is 0. So my answer is going to be a quarter, 17 over 4, and 5 over 3, 0. And this is going to help me in the second part of this question. So now this question's we've got the part B on here now. Use calculus to find the exact area of R. So we can see here, we've got our diagram again. And we know, obviously that's the origin, and we've got this point P here with coordinates a quarter and a y coordinate of 17 over 4. That's going to massively help me in a second. And I know it's crossing the x-axis here again at 5 over 3. Now to do this, if I want to find the area, you might just think, okay, it's all calculus, it's all going to be integration here. But I can't just simply integrate this with limits of 0 to 5 over 3. That would just tell me the area under the curve. Neither can I just do between 0 and 5 over 3 under the curve and then do 0 and 5 over 3 under the line. What I'm going to need to do is I'm going to need to split this up into two areas. I'm going to call this A1 and this A2. And what I've got here is between 0 and a quarter, or my area for A1, I'm looking at the area under the curve. Between the quarter and 5 over 3, I'm looking at the area of the triangle that's created there. So firstly, I'm going to find a 1. So this is where I'm just exclusively looking for the area under the curve, okay? Between 0 1/4, all of this area under the curve is just going to be, let's say between 0 1/4, it's just the area under the curve I'm looking at. So I set this up, put my limits there of 0 1/4, and then I put the quadratic here, and then put dx. When I integrate it, I put the square brackets. That should be a 20x. So the 20x, when I integrate that, I get 10x squared. So raise the power of x by 1 to get x squared, then divide by the new power of 2. And then the minus 12x squared, make that an x cubed, and then divide by that new power, so you get a minus 4. We don't need plus c here, because when I come to evaluate the limits, the c's would cancel out anyway. So I substitute x equals 1/4 into here, and I get 9/16. So I put in 10 times 1/4 squared minus 4 times 1/4 cubed, and I get 9/16. Then put in x as 0, and I just get 0, meaning that the area under the curve is going to be 9/16. For the triangle, we simply work out the length of the base here. So to do that, we do 5/3, take away 1/4. Okay, so just look at the diagram. I just want to work out this length here. And then I would times that by the height, okay, which is just going to be 17/4, because it's just going from the base where y is 0 to where y is 17/4. And then it's a triangle, so then just got to simply times it by 1/2. So I'm going to multiply that all together. Of course, we can do this, the whole of this paper, we can do it all on our calculator. So we just simply shove that in the calculator. And then to work out the total area, all I do is just 9/16, so the area of A1, add the area of A2, and again we just put this on the calculator, and we just get 343/96 as my answer. I was asked for the exact area of R, so I would just simply leave it as that improper fraction there, rather than change it to a decimal.